Assalamu alaikum. Let's start with a new topic, chapter 10. And this chapter basically is named as second moment of area and moment of inertia. Okay, this is our new chapter, second moment of area and moment of inertia. Okay, basically, second moment of area is a term which is very much widely used not only in statics when dealing with basically mechanical structures. It's also used in fluid mechanics, and basically when we are designing beams we will be using this second moment of area a lot. Okay, so what basically second moment of area, basically it's a function of about the two axes, the x-axis and y-axis. When we need to calculate the second moment of area about the x-axis, we call it as Ix is equals to integral of y square dA, and when we need to calculate the second moment of area about the y-axis, we will always use the formula Iy is equals to integral of x square dA. Okay, now the first question that will arise into all of us mind is that why we call it second moment of area. Okay, so the answer lies when we were studying chapter 9 and we have finished at chapter 9. Remember when we used to find the x coordinate uh, of any basically composite or any basically any component, or so we what we used is basically x bar is equals to integral of y tilde dA divided by integral of dA. And when we used to calculate the uh, x bar of any basically composite or basically curve or shape we need, we used to basically use the formula integral of x tilde dA over integral of dA. But if you look the numerator, this numerator integral of y dA and this numerator integral of x dA, this is termed as the, if you look at it here, is called the first moment of area of the cross section. It will always be whatever cross section or whatever basically object is given to us, whatever either it's a shaded area and it's not a fully geometric shape, so we'll use integral. And we know when basically we are using a composite shape or basically we will using a summation sign. So we use this thing when we have using a shaded area given to us. For that we use the integral sign as we have told. So for any cross section, any shape that is given to us, it would be termed as the first name as first moment of area, y integral of y dA, that is why. And if you look here, when in chapter 10 we call it Ix equals to integral of y square dA and Iy is equals to integral of x square dA. So what this is called as the, this thing is called as the what is it called, it is called as the uh, second, it will be termed as the second moment of area. ओके, सो इसको हम क्या कहेंगे, सेकेंड मोमेंट ऑफ एरिया कहेंगे. So you must always remember that Ix equals to y square dA integral, and whatever the limits will be there, you have to apply the respective limits, and Iy will be equals to x square dA. And remember dA over here, dA will always be calculated as a differential strip. dA will always be calculated as a differential strip of rectangle which has a specific length and specific width. Okay, exactly the same way in which we are calculating the given shaded area basically during a centroid calculation of chapter 9. So Ix is the explanation of this. So for composite physical concepts is very important of this. Actually, whenever we are doing beam designing, anything related to beam design, we will, as I told you, we will be using it this. Okay, so second one to cross section is the ability of the cross section to resist bending, okay, or wrapping around the cross sectional area. So what does actually it means, that whenever load is being applied over a beam, it will try to bend the beam over specific basically its cross section will be bent about because of this loading. Okay, and what does this load tries to do, it basically tries to wrap this beam uh, about the basically cross section, about its respective cross section, which is basically the, if you can say, this is the about the x-axis, it will try to wrap it about. Okay, so this is what is thing. And if this load is basically very high, so it will try to bend the beam more. Okay, so but on the contrary, if we design the beam in a very well professional way, and if its moment of inertia is high, Okay, if the value of the moment of inertia, whether we are calculating Ix or Iy, and these values are higher, then when the load is being applied on the beam, it will bend very less. The bending will be less, and will be resulting in less deflection, and your structure will be more safe. Okay, so this quantity tells us that whether we are taking an I section beam, or here it is I section beam or a rectangular beam, this is very important quantity, because it has to be designed very accurately. Otherwise your structure can fail and can result in catastrophic failure, and human lives could be lost if it is not accurately designed or calculated. Okay, so the quantity is essentially calculated when designing where it is structural members like beams, not only beams but shafts and columns. Okay, so basically in columns use it, and the Euler's equation, okay, Euler's beam equation हम उसको use कर सकते हैं, in shaft design में कर सकते हैं, machine design lot of basically has applications of movement of area. Okay, and basically again remember this quantity second moment of area is basically a geometric property, which means it all depends upon the geometry, a function of the geometry of the cross section. It will vary from one cross section to another. A more better and precise cross section will have a higher moment of area compared to the one which has a bad cross section will basically have less resistance to bending. Okay, so these things are very important. Degree of the bending of the beam can be altered if the dimensions of the cross-sectional area are altered. In other words, if the second moment of the beam cross-section can be increased, its bending can be decreased. It's a vice versa relation. Higher the second moment of area, lesser will the bending, and if lower the second moment of area, the bending will increase. And we do not want that being mechanical engineers. Okay, so then comes a very important theorem which is called as the parallel axis theorem. Okay, so we know already the formula. Okay, the second moment of area basically is calculated. Okay, before this, what I will do is uh, your book. If I look at a book, this is your book. Okay, R.C. Hibbeler. It says the moment of inertia by definition is being defined as dix equals to integral of y square dA. Okay, so if you integrate y square is a constant, so integrate dix will get ix, and integrate dA we get a. Okay, so ix equals to integral of y square dA, and iy equals to integral x square dA. How it is basically being taken in a cross section, you must remember. Here we have the two axes x and y, and here is an arbitrary shaped body. Okay, so whose basically over there we take a differential element dA. Okay, and the differential element perpendicular distance from the x-axis is given as y, and this differential dA element which is taken, its horizontal distance from the y-axis is given as x. Okay, so for this arbitrary cross section, because it's not perfect geometry, we will use an integral sign. If we want to calculate the moment of inertia about this axis, say about the x-axis, so it will called as Ix, moment of inertia about the x-axis. So it will be Ix is equals to integral of a, okay, integral of a y square. This is single y, so it's y square times of dA. And if we are interested in calculating the second moment of area about the y-axis, so Iy, about this axis, so we'll call it integral of a x square dA. Okay, so that this basically explains the physical significance of Ix equals to y square dA integral and Iy equals to integral x square dA. So what actually means by that? Okay, so now we can turn our attention to the main topic. So we understood this. Now again we have a differential area dA, and we have basically two axes. We have two axes. First we have two axes x and y. Now for this, if we have two axes, and we have already calculated the centroid of this arbitrary cross section is C. Okay, so the second moment of area is always calculated about a certain axis. We know we have just taken the practical picture in the previous book of our R.C. Hibbeler. This axis can be the centroidal axis of the cross section. Okay, and on the other hand, this axis can be other axis as well. So the parallel axis theorem, as the name suggests, can be utilized in calculating the second moment of area of the cross section about any axis that is parallel to the centroidal axis of the cross sectional area. ठीक है, अब इसका मतलब क्या है? What is it trying to say? Okay, he is trying to say that if we have calculated the second moment of area, say about x dash axis, okay, but he is not interested. We already have calculated the second moment of area about the x dash axis, but he says he is interested not in this ix dash axis, second moment of area about the ix dash axis. He says he is interested in calculating the second moment of area about this axis, which is x. Okay, so we have how many basically axes involved? Two axes involved, and we basically have calculated second about one axis, but now we want to calculate the second moment of area about the other axis. Now if you look at it, this axis we already know, okay, ix dash, and this axis is basically exactly parallel to this axis. Okay, so what is the theorem called? The parallel axis theorem. Okay, and on the other hand, if we have basically calculated the second moment of area y dash, okay, we have calculated the second moment area about the y dash axis, but we don't want it on this. We want the second moment area calculated about the y axis, which is exactly parallel to this. So we will be using when two basically axes parallel to each other are involved, and we are basically wanted the second moment area on another axis which is parallel to it, so we will be using the parallel axis theorem. Okay, so it's very simple. So if you look at this ix is the very important. If you look at it, what is ix? Ix is the second moment of the cross sectional area about the x-axis. Ix dash is the second moment of cross section about a centroidal axis x dash. This C is the centroidal axis on what is the axis? X dash. Okay, and the formulas for the simple shapes is available. Okay, so A is the cross sectional area. What this A overall A is the cross sectional area in which we have taken a differential area dA. And very important thing, from the centroid, from the distance between the two centroidal between the centroidal axis and the axis on which we need to calculate the second moment of area is termed dy when calculating ix, and the basically distance between the two axes when we calculating the moment of second moment of area about the y axis. Okay, we already know the moment about the second moment of area about y dash axis, and we wanted to calculate about this. So the perpendicular distance between these two parallel axes is from here to here is dx, and on the other, for when calculating ix, it is termed as dy. This is very important. Okay, dy is the perpendicular distance between the two respective axes which is under consideration. Okay, which these two axes are over consideration. So basically for parallel axis theorem is also exactly the same as basically the one we have just done it, like you know, we know that ix, what is ix? We know what is ix. Ix is basically nothing but y square. It is y square, and you know what was dA. Remember, it is this y square dA. So dix about this axis, if you look at it, this will also be as y square dA. So it is very similar. It is similar. But since over here, if you look at it, basically we are interested in calculating the second moment of area about another axis, which is the x-axis. Okay. So basically, how we will calculate this over here? We will calculate this by calculating the moment of second moment of area dx equals to y dash plus dy square times of dA. Okay, so what does it means? So y dash is basically, if you look at it, a plus b the whole square times of dA. Okay, so we can basically, if we integrate both sides, so dix will becomes ix, and integral of dA becomes dA. Okay, so if we can integrate this side, we can get it over here, and basically here we can say integral of y dash plus dy square times of dA. So we cannot basically directly integrate it right now because of this function. Okay, so we cannot do that. Here we can get ix. So but if you look at it, this is a plus b times the whole square times of dA. So we can basically very easily calculate. And okay, now what is this basically? If you look at it from here, this y dash plus dy the whole square. Okay, so basically if you look at it, what is basically your specific y dash? Basically this is your y dash plus dy y dash plus dy the whole square times of dA. So when we basically expand it through formula of a plus b the whole square, it will become y dash the whole square, okay, plus 2 basically dy integral of y dash dA, and again this one will become plus dy square times integral of dA. We can very easily by means of we have expanded it. Okay, now remember one thing, that this thing 2 dy integral of y dash dA, this term, okay, this term is very important. We will say this term will be 0. We will say this term will be 0. We will call this term as we will call them as 0. Why 0? The reason being, just tell me what will be the values of the coordinates x bar and y bar at the centroid at this point. The values of x dash and y dash at the centroid. What will be the values? Because we'll start from here, we can go here, we can start from here, but what will be the values of x dash and y dash at the centroid? They will be 0. So integral of 0 times dA will be what? It will be 0. So we will say this value will get vanished. Okay, now we are left with this value and we are left with this value. Okay, so this value, which means now what is the meaning of this value? So ix equals to integral of y dash square dA. What does this means? This value, if you look at it, what was y square? We have just calculated what was y square dA. Just a formula you already know. What was y square dA? What was y square dA? It was ix. So what will be y dash square dA? What will be basically y dash square dA? What will be the value of y dash square times of dA? Okay, it will be nothing. This value will be nothing, but it will be written as this value. It will be ix dash, because why? Y square dA, basically if you can also put an integral sign here also. Ix equals integral of y square dA was ix. So y dash square, because dA will be what? About it will be ix dash plus integral of plus dy square times integral of dA. It will become integral of dA will become a d square y. It will become a d square y. So this is basically called as the parallel axis, how you basically apply parallel axis theorem for the solution. Okay, so exactly basically right now we will engage in ix dash and ix. So if we want to calculate the second moment of area about the iy axis, and here we will already have the moment of area for y dash. So we will be taking it, we will be writing it as iy is equals to iy dash plus area into d square x. Okay, if you look at it, there is very much similarity between the two, ix and iy. Here it is ix dash and here it will be iy dash. Okay, so iy dash will be basically what? If you can say, it will be integral of a x dash square dA. Okay, and remember this dx square here will be, it is this value. When these two x's are involved, this is going to be your dx. Okay, when we were calculating ix, we were using at d square this value. Now we were using this one because we are calculating iy. Okay, and this is the same as iy dash will be equals to integral of x dash square times dA. So this theorem is very important when we are basically already given the second moment of area of one axis, and they ask you to calculate the second moment of area at any arbitrary axis. Okay, so it is not only this axis. We can also say, if we have another axis here, you remember, if we have another axis and we have another axis here, so he can also say, I call this axis as x1, I call this axis as x1, and I call this axis as x2. Okay, so again the logic will be there, same. This distance will know dy plus some distance, you can say that distance as dy double dash, if you can say whatever you want to say, you can, it will be this distance, and it will be this straight distance here, and you can calculate the second moment of area about this axis. You can call this any axis as s, for example, you can call it as x double dash axis. So as long, how many axes are there, just apply the parallel axis theorem and solve it. You can also do it along this, as you can call this axis the new one as y double dash. You can calculate iy at this y double dash axis. Okay, so I hope you understand the parallel axis theorem and the second moment of area in very simple terms. And to understand, just to understand another important point, if you take your steel ruler from which you draw a line, okay, if you hold it parallel to the table on which it is lying, and you try to bend or the two ends by holding your hand and try to bend it, you can bend it very easily. But if on that same table you make that uh, scale or ruler perpendicular, okay, perpendicular to the table on which it's lying, okay, and then you hold it on your both from the both hands and try to bend it, you will not able to bend it, because the reason being this, before your, when you were applying the bending, its second moment of area was very low, and you know when low second moment of area is there, it means that the bending will be very great. But on the other hand, if the second moment of area for the second case in which it was lying perpendicular to the base of the table, now the second of moment of area will be increased. Okay, so when the numericals will come, and in the class I will show you also practically how it could be done to apply this practical example and to understand the real importance of the second moment of area in designing of mechanical structures, civil structures, automotive structures. It's applied a lot over there. So being mechanical engineers or any type of automotive, civil engineers, manufacturing engineers, you need to calculate, you need to understand the second moment of area and parallel axis theorem. Very important. Okay, so it is a very important, not only from your first year, but in when you go second year, third year, final year, you will be applying the parallel axis theorem, the second moment of area, the first moment of area, the centroids, a lot. Okay, in subjects like dynamics, solid mechanics 1, solid mechanics 2, machine design, machine dynamics design, mechanical vibrations. So you'll be applying them a lot. Okay, so we finish here, and then we'll come with a new topic of chapter 10, which will be called as the moment of inertia. Okay, thank you very much to all the students. Jazakallah. Allah Hafiz.